In this video, we're going to show how to integrate an absolute value function. So let's jump in. Okay, so go ahead and pause the video and see if you can integrate this by hand. Okay, coming back, here's the answer, 2.5. If you're able to get that easily and, multiple methods to get that result, feel free to skip the video. Otherwise, we'll dive into it here. The first way that you can integrate this is with what's called geometric integration. So whenever you're trying to integrate an absolute value function, hopefully it makes sense that you can always break things down into triangles and sometimes also rectangles if it's shifted up or down. In this particular case, it's clear, I think, that we have a 1 by 1 triangle right here. So what's the area of a 1 by 1 triangle? Remember, the formula for the area of a triangle is 1/2 times base times height. So 1/2 times 1 times 1, that's just 1/2. So the area of this region is just 1/2. And then over here, we basically have a 2 by 2 triangle. What's the area of a 2 by 2 triangle? 1/2 times 2 times 2, or in other words, 2. So that's how we get 2.5 as the answer. Even if you add like a vertical shift outside, you can still do this. So for example, hopefully it's clear that we still have the same shape that we did before. We still have these two triangles. So this is still a 1 by 1 triangle, which has an area of 1/2. This is still a 2 by 2 triangle right here that has an area of 2. So this, we still get 2.5 on top. The only thing that's changed really is that you can imagine us adding a rectangle at the bottom that has a width of 3 and a height of 3. So, and it's actually a square in this case. So the height would be 9, for example. So that's why we would just add 9 for this rectangle to the old 2.5 that we got above, and that's how we get 11.5. So you can do this technique with any absolute value function and a lot of other functions too. Like if you have constant functions, you can use rectangles. If you happen to have circular functions, you can use circles. If you have linear functions, or like y equals mx plus b, you can always use triangles and maybe a combination of rectangles to solve it. But that's geometric integration. So there you go. Geometric integration is always an option with absolute value functions if you understand exactly how to graph it. But ideally, we'd also like a method besides geometric integration. The big issue, though, here is what do we do with the absolute value bars? That's the question we need to answer to be able to solve this purely by hand without graphing at all. Now, to actually deal with this, remember what the definition of the absolute value function is, specifically the piecewise definition of the absolute value function. If you have a function x and you're trying to take the absolute value of it, think about what that really means. We can think about it as a piecewise function where x is, or where the function is just equal to x if x is greater than or equal to 0, and it's negative x if the function is less than 0, or if the input is less than 0, I should say. Why does this make sense? Think about what would happen if you actually plugged in an input here, so like 3, for example. Well, if you plug in 3, 3 is greater than 0, greater than or equal to 0, so it would be according to this function, and then they're telling us that the output would just be 3. So doesn't that make sense with the absolute value? The absolute value of 3 is 3. In other words, just leave it. If you plug in negative 3, on the other hand, that would fall into this situation because negative 3 is less than 0. And then you multiply negative 3 by negative 1 to get positive 3. So the input would be negative 3, the output would be positive 3 again, which actually, if you think about it, is the correct behavior. The absolute value function just flips it positive if it was negative originally. And that's all this is really doing. All this piecewise function is saying is that if it's positive, if the input is positive, just leave it. That's the output. If it's negative, multiply by negative 1 to flip it back positive. So that's all the absolute value function does. So hopefully it's clear that this actually is correct. Now, if you want to take the absolute value of more complicated things like we have here, so we have x minus 2 on the inside, not just x, basically all you have to do is just take this definition and just every spot that you see x, you can just blindly replace it with x minus 2 or whatever is on the inside of the absolute value bars. So let's do that. If I do that here, hopefully it's clear that I'll get x minus 2 right there, and I'll get negative x minus 2 right there. And then for here, I'll just get x minus 2 greater than or equal to 0. And then I'll get x minus 2 less than 0. So there you go. This is the piecewise definition of this absolute value function, the absolute value of x minus 2. Now here, one thing you probably want to change with these inequalities, you probably want to solve them to isolate x. That'll make things make more sense. So basically, if I add plus 2, to both sides of each of these inequalities, you can solve them just like equations, basically. Well, there's one rule that is new, but I won't go into that right now. But basically, if I add x plus 2 to both of these, hopefully it makes sense, that I actually get x is greater than or equal to 2, and I get x is less than 2. And this is what we normally think about as the piecewise definition of something like this. You could also simplify this if you wanted to be 2 minus x, but you can also leave it the way it is now. So here, let's test this. What does this actually mean? It means that basically whenever x is, whenever x is greater than 2, so like over here, it is literally the function, the output is literally the function y equals x minus 2. Does that make sense? Actually, yes. What would y equals x minus 2 look like? It would basically look like a linear equation with a slope of 1 and a y-intercept of negative 2. So if you start off at 0, negative 2 and go up 1 over 1, up 1 over 1, hopefully it's clear why, yeah, that actually does seem to be the function that we're graphing here. But again, we're only turning it on when x is greater than or equal to 2 here. We're not including stuff down here. That's why I left it dotted. So hopefully that's clear. This function, think about what this would be. This would really be negative x plus 2, if you want to think of it like that, for the negative side. So basically what that means is that when x is less than 2, so all these values, this would look like the function negative x plus 2. So y-intercept of 2, slope of negative 1, down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. Yeah, that actually does seem to be what we have graphed here. So hopefully it's clear that this piecewise definition of the absolute value function is literally the piecewise. You can literally think of it instead of an absolute value function. You can think about it as this piecewise function that is literally what we're seeing here. And this is a whole lot easier to integrate than the absolute value function. So if we can think about this absolute value function as this piecewise function, that's important. But there's also another thing that we need to know, and that is this integral property. Basically, this integral property, whenever you have a definite integral, whenever you're trying to find the area under the curve of f between x equals a and x equals b, basically all this is saying is that you can split it at any point you want in the middle. And hopefully it makes sense that the integral between a and c, wherever we decide to split it, c can be anywhere on the inside. That would just be the purple area. And then the integral from c to b, that would be the green area. And if we just added up those two separate areas, that would be the same thing that we would have gotten if we didn't split it, basically, and just treated it as an entire area from the get-go. So hopefully that's clear, but this integral property in particular is also going to be helpful to us. Specifically, the way that we're going to use this integral property is to split it at the transition point of the piecewise definition. So remember, in this particular case, the piecewise definition switches from this function to this function at x equals positive 2. So why don't we just choose that as our transition point? And then we know that when we're less than that, the piecewise or the absolute value will equal this version of the piecewise function, negative x minus 2. And when x is greater than or equal to 2, it will equal this version, just positive x minus 2. So there you go. We can take this integral, and using the integral property and the piecewise definition, we can set it up like this. And now we basically just have to solve. So if we solve this, think about how this would go. You could just take the integral of both of these separately. So with this one, and here's another trick, by the way, that you can do with these. You can pull out a negative. So I'm just going to pull this negative out. And the reason that you want to do that, the reason that that's helpful is because then if you think about it, you'll actually have the same integrand on the inside of both of the functions. So you have different bounds, of course, but at least you'll have the same integrand. So you only have to find the indefinite integral once, if that makes sense. Now here, let's actually do that. So if I was trying to find the indefinite integral of x minus 2, the positive version, what would that be? Hopefully it's clear that it would be 1/2 x squared minus 2x. And you can take that, if you want to double check that, you can take the derivative to verify that we get the x minus 2. We don't need the plus c here because remember, this is a definite integral, so we're going to use these bounds. So basically, what is this going to be? It's going to be negative. So this is going to equal negative. And then this function evaluated at 2. So what is that going to be? So that'll be 1/2 2 squared minus 2 times 2. And actually, let me separate this a little bit more. So the first integral will be that minus the integral evaluated at 1. So 1/2 times 1 squared minus 2 times 1. So hopefully that's clear. That's the first part. That's this first integral. And then the next part is the second integral, which will be plus the integral, basically evaluating this function between 4 and 2. So that'll be 1/2 4 squared minus 2 times 4 minus 1/2 2 squared minus 2 times 2. So there you go. Now, what would this be? If you think about this, it would equal negative, basically 1/2 times 4 would be 2 minus 4 minus 1/2 minus 2. So that's that one. Plus, this will be 4 squared, 16, divided by 2 is 8. So that'll be 8 minus 2 times 4 is 8. So that's actually convenient. That cancels out. And then we have minus 1/2 times 2. So that'll be 2. And then minus 4. So there you go. We have that. And if we simplify this, let's see what all we can simplify here. That goes to 0. So that's a plus. So, and this will be just plus. So 2 minus 4 is negative 2 times negative 1 is positive 2. And then we have a negative out here. That'll be a negative 2. And then this, think about what this will be. This will be, it'll be, so 1/2 minus 2 is negative 1/2. So, but it'll actually be plus 1/2. So, or 1/2. So actually I'll say 3/2. So what's negative 2 plus 1/2? Negative 1/2. But remember, we have the negative here. Negative 1/2 is positive 1/2 plus 2 equals 2.5, 2.5, which is what we got originally through geometric integration with triangles. So there you go. You can see the same answer. You can see that with this method, integrating purely by hand without even graphing it at all. You don't have to graph it at all to do this. You can just do it purely symbolically, but we get the same thing that we did with geometric integration, which is what you should get if both of the methods are valid. So there you go. That's 2 separate ways that you can integrate any absolute value function. Hopefully that makes sense, and I'll catch you next time. See ya.